real machine learning, especially optimal transport inside. So as you are all aware, I guess, attending this DEGA seminar, which is a very nice initiative in this past few months and years now, graphs are structures that are very useful for data processing. And so I've just put forward here a few examples, be they taken from what we call globally networks, complex networks, such as social networks or actual networks like electricity, water, or communication networks, or the representation of data coming from physics or chemistry. You have all done a little bit of chemistry, possibly younger, and we draw these nice graphs representing molecules. And the same, we can look at different types of images, 2D images, point clouds, but other geometrics, other types of images as being supported on the graphs. And so there is globally this question of how to deal with attributed graphs. Just to set the vocabularies, in general case, we have nodes, possibly edge also, carrying information in addition to the existence of the pairwise relation between the nodes. The fact that we have some attributes at the level of nodes, here a very simple example, that we have weights, for instance, distinguishing between high interaction between here, in the example, node U1 and U4, or U2 and U3, and lower interaction between U1 and U2. All that is well coded into the graph and its attributes. So we have the adjacency matrix, the attribute matrix of a certain size, and we want to combine all the information, the relations that are coded by the graph description of this data, and also the attributes or features. I'm coming from a background of signal processing. I would say often there's a signal on the nodes. We can generalize that on signal of edges. Here will be limited to have signals or features or attributes, equivalent word in this talk, on the nodes, and a weighted adjacency matrix describing the relations between the entities. So in machine learning, since quite a long time before we were doing graph signal processing, they were interesting in solving different tasks for data on graphs. Even though they didn't have always the good approaches for that, but at supervised tasks, they want to learn to classify nodes. They have one graph, for instance, with in a semi-supervised setting, some nodes with a blue label, other nodes with a red label, and you want to infer what is the label on the white node while you don't have the label initially. You can learn to classify the graph when you are dealing with a collection of graphs, and you play the same game. You can do unsupervised clustering. You want to find what is the criteria to separate different nodes in groups that are coherent. On the left, you find clusters, and it has a big history in network science when you find modules or communities in complex networks. On the right, it's more a vision of machine learning where you have various graphs with attributes. The graphs, for instance, could be the small images of one of the challenge of computer vision, MNIST or another one. Then you want to classify these small graphs, saying which one appears to which one is in which cluster. There is a whole interesting discussion to do when you want to take into account more general features of the topology of the graph, the existence of small world properties, of scale freeness, of hubs, of higher order interaction, and so on and so forth. I will not deal at all with that in this talk. I will mainly really focus on this idea that we'll have a graph, we have features, and we can combine them to extract some information from the graphs. So, one way to do that is to rely to the global set of techniques of representations or embeddings of graph. Again, this has a long history. First, initially to visualize complex graphs. For visualization, people have used in the past 25 years many interesting methods, going from Laplacian maps, linear local embedding, physics-inspired algorithms such as ForceAtlas, or more machine learning techniques such as t-SNE, UMAP. Here, just a shameful advertisement with the work we did with Nicolas Tremblay about community detection using GSP and wavelets on graphs. This is good for visualization or finding globally the structure in clusters. From the machine learning perspective, people have put forward the existence of high-dimensional embeddings where you can leverage all the recent advances in deep learning, especially where you encode the nodes of the original network in a large dimension embedding space, and then you work on this space to solve this task of classification or clustering. And when you want to embed globally a graph, usually you will embed the node and then concatenate in some way the embedding of the node. So again, something that I guess is very familiar to all of you. In the past now 10 years, there have been an extension of representation learning for graphs, but globally in machine learning, to say that we can discover or learn the adequate representation for data, and that's a good way to extract the information and to solve the task that we have about clustering or classification. In the good old days, machine learning was try to find a function which, from an input X, gives you a decision map to a classification, for instance, Y. It is either the class or the number of the cluster. It can be in regression setting a value and something like that. And it has been shown recently, in the past 10 years, that instead of doing uncrafted features using your knowledge of the domain, you can learn from the data both the decision function and the feature representation function. And even if you want to do that in layers, you go to the domain of deep learning. And here I've taken the figure from the books of Goodfellow, and it seems something that is, I guess, well known to all of you. And so for graphs, we have exactly the same thing. We can represent nodes in the graph and give an embedding for each node, or we can try to design a way to embed the graph globally, again, as a Euclidean vector in some space. Usually for graphs, you agglomerate or you concatenate in some sense the representation of the individual nodes, possibly by taking into account from one node to another the relationship of adjacency. But anyway, you can do that, and you can combine a model of classification and model of representation, define a task, a data set, learn and see what happens, and usually you have good results. The great framework of graph neural networks is a very good way to do that. You learn a new representation of the graph by a combination of usually filtering and agglomeration and putting in the graph. In what I will present here, still for this, this is a low-level I said it's a this graph representation learning is a low-level task because it's really the task of representation, and then you can adapt it to many different tasks. There are some associated difficulties, as we know, at the level of nodes. The structure is inhomogeneous, so it's hard to compare two nodes. We have ways to compare two nodes, but if you take them either all the importance of this work in representation learning of graphs is to know how to compare the nodes. And at the graph level, we know that there is a difficulty that there is a possible isomorphism, which is hard, a question hard to solve. It's hard to compare or to confine the equality of two graphs. It's a well-known problem of finding whether two graphs are isomorphist, even though we know that they have good heuristic algorithm, and I will say a word about that just as that. And so now if you want to turn to attributed graphs, that means in graphs with graph signals on that, we want to combine the structure and the attribute. And even the structure at the node level or the graph level, it's a little bit difficult to cope. And the attributes, we have all a bunch of literature of how to compare the attribute using suitable distances. So we decided to take a different view on that. We said, instead of focusing on the embedding method or representation method, we want to focus on the method based on the creation of distances or the measure of similarities or dismissed similarities in graphs. And we know that instead of finding a full representation space, just the comparison graphs can open the possibility to use many methods for attributed graphs. This is a trick that is well known since people were doing machine learning, let's say with kernels, with distancing. You say, if you build a good distance between two entities that you want to compare, X can be a graph, X prime another graph. If you have a good and representative distance between them, then you can use many different methods, SVM, like in the 90s, KNN, but still, this method have good performance. SVM still can beat representation methods if you put good distances or good representation. KNN are still efficient because they are very scalable. You don't need retraining. And so if you want to deal with a large data set, you can still use that. There are other methods you can rely on if you have a good distance between your objects. The disadvantage of doing that is that the direct comparison of graphs is difficult. If you want to use existing distance that are well known, such as a graph edit distance, where you are counting the number of changes of edges that you are doing from one graph to another one. Theoretically, it's an ampere-hard problem. There are heuristic approximation, but still there is a work to do if you want to scale that on a large potentially on a large data set. So to focus on the creation of distances between graphs, between attributed graphs, what we did is we decided, because we were working between two groups, the groups of machine learning in Saint-Etienne and our group in graph signal processing in Lyon, we decided to use the tool for machine learning they were very familiar with, that is optimal transport, and that had been put forward again since 20 years ago as a tool which is good and generic to discuss distances between probability measures, to create distances and to solve many questions about things that you can frame as a distance between two distributions. Can be used in equalization between histograms in image processing. It was initially discussed in image processing 20 years ago as a Earth mover distance. It has been used by Julie Delon and then Gabriel Perret in Paris to do many smart things in image processing. It has been not rediscovered, but Cédric Villani wrote a large book in 2003 showing how in many domains of mathematics and statistics it can be used. It's related to the Mallows distance in the statistics. We even used that with Patrick Flandrin and Patrice Abri 10 years ago in a completely ignored article to do non-stationary processing and things like that. So anyway, since 10 years back, in machine learning, especially thanks to Gabriel Perret and Marco Cucciuri, and they have written this nice book about computational optimal transport. The mathematics are well known, and it has been put forward as a good computational tool to compute distances between distributions when you are able to code the object of interest as a distribution. If I'm taking here a slide from the Norris tutorial done by Couturier Salomon 5 years ago, you can address all these things using optimal transport. You can compare statistical model. If you have two distributions with two different parameters, you can compare them and associate a distance between the two distributions, hence between the effect of the two parameters. You can do that also on generic, here it was bag of features, but now you can do that with more advanced representation from NLP. You can do that on brain activation maps. You can compare a generative model, the distribution of the generative model and the distribution of your data, like it has been done by the group of Julie Delon. You can compare histogram of colors and many things which are really interesting. And this can also be done on graphs. So before moving back to attributed graphs, I'm giving you again a few ideas coming from this domain of optimal transport for distribution. So initially, it's an old problem. This one, a very old problem. It's not 20 years ago. It's 250 years ago. The problem de Monge about mémoire sur la théorie des Debré-Ramblay. That means is document about how to move Earth. You have a Ramblay here. You have Earth somewhere, and you would want to put it so as to make the sun planar, and you want to do that with a minimum cost. And he was asking how you do that. What do you move to where? So this has been a nice mathematical problem, and it had a very elegant mathematical solution, especially the one with the relaxation of Kantorovich, when you say that you will not move discrete measures, but continuous measures. And one solution is to find a transport map. This is the optimal transport, which maps this blue distribution to the red distribution with some maps which will have a minimum cost. So mathematically, that means you are considering two sets and their associated distributions. Here, mu and nu, you normalize this thing, and you want to find, given a cost function, which is the cost of displacement of your distribution, so the displacement of Earth from one place to another one in the Monge problem, you want to minimize the full cost of displacing the initial distribution toward the target distribution according to this cost, and P, ij, is the coupling, saying that you are moving a part of the distribution from I to J. And you minimize that, you try to find the minimizer of this cost function, and this gives you what is called the two-Wasserstein distance of the distribution. For this cost function, you have the choice of the cost function, and in fact, you also have the choice of the norm. Yeah, I'm just using the two norm, but you can have the p-Wasserstein distance if you prefer. By respecting these constraints, and the advances in the past 10 years, especially by Marco Couturier, was to show how to efficiently compute this thing, for instance, with an entropy regularization. I will not use that here. So, if you are able to do that, you both have the plan, which is the argument of this minimum, and a distance between distributions. So for graphs, the question was how to associate a distribution to a graph. And many people already proposed ways to associate a distribution to a graph, so as to leverage the tools of optimal transport for a graph. So the first solution was to rely on the well-known Weisfeller-Lehmann test for graph isomorphism, which has also been put forward in development of graph neural networks, in Gene especially. Tognali proposed to build a graph kernel by combining Wasserstein distance and Weisfeller-Lehmann approaches. This Weisfeller-Lehmann tells you when you have a graph here, you will consider the graph and its neighborhood, each node and its neighbors. That means this vector, this other vector for this node, and so on and so forth. And then you are hashing the structure, the local structure, encoding the topology on each node. You obtain some value, and you iterate, that. So the k times, so that means you will encode the topology up to all the k ops in the graph, and you obtain a distribution which is not exactly characteristic of the graph. There are ways, there are well-known examples where you find equal distribution at the end, even though you have different graphs at the beginning, but still it's a good heuristic to solve this question about graph isomorphisms. So it has been proposed that it's a good way to build a distribution representative to the initial graph when you have an unweighted graph, an unattributed graph without any attributes. Another thing that has been proposed by the group of Pascal Frossard at EPFL is to compare the graphs through the probabilistic modeling of the graph signals that you can have on a graph. We know that there is a class of graphs where there's a class of signals that you can draw on a graph, which are the Gaussian, the Gaussian Graphical models, in a sense, taken as a Gaussian distribution with a variant which is the inverse or the pseudo-inverse of the Laplacian of the graph. And this is a generative way to have signals which have control properties on the graph. And now you can use this set for these models of random signals on the graph to compare different graphs, and you can compute the two Wasserstein distance between the Gaussian signals that are each representative of the graph, and it gives you a meaningful distance. And they have used that to solve questions of graph alignments, especially. There is a third approach that has been proposed, especially in the PhD thesis of Tito Envaheur with Nicolas Courty and Rami Falmari, where they were using the Gromov-Wasserstein approach, which has been put forward by Memoli, which generalizes a little bit the Wasserstein approach. That means you will not directly try to compare the initial distribution mu and the target distribution. You don't create, in fact, directly a cause between the nodes. What you are comparing is the topology of the initial distribution and the topology of the target distribution. And one way to define what is the topology of the distribution is to use a Gromov approach coming from geometry. And you say, but the topology for distribution mu is all the set of pairwise distances in your initial data. And the same for nu. And the good way to do that is now you don't need to have the same number of elements or the same geometry or topology at all in X and in Y. You can have a set of pairwise distance on one side, another set of pairwise distance on the other side. It's not the same number. And you compare for all XX prime in your initial measure and all YY prime in your target measure, all these pairs of distances. The good thing is, so you can do that on graphs. They have shown that you can easily combine this Gromov-Wasserstein approach to characterize the graphs with the attributes when you combine this distance between the pairwise distances and another distance between the features on the node on the initial graph, AI, and the features on the node on the target graph, BJ. And you can combine these two with some parameter, which is a trade-off between the structure and the attributes. This works well. The bad points about doing that is now you have an optimization problem to solve to obtain the minimal transportation cost, which involves a sum over 4 nodes, 2 nodes in the initial distribution, 2 nodes in the target distribution or graph. And so you have a computationally heavy approach of this thing. And the second thing is now you have a trade-off between structure, so through the Gromov-Wasserstein and attributes, and you need to solve this trade-off. And there was no good way at that time to really solve the trade-off. It is a hyperparameter, and we didn't know what to do about that. So after this introduction, trying to convince you that there are things that we can do using optimal transport. Now we can also combine that with the insight that we have from graph signal processing, the fact that we know how to manipulate signals on the graph, and that we can do that to solve several questions. And we'll put here the focus on 2 different works we've done on that. The first one is really to define a distance on attributed graphs using optimal transport and heat diffusion of the graph. And the second one, in the last part of my talk, will be about doing metric learning for graphs in a scalable way. And all this work were done jointly with the group of Marc Seban and Amaury Abrar at Saint-Etienne. So they are the specialists in machine learning. From our side, we'd say we are more from the background of graph signal processing with Paulo Gonçalves and Remo Gribonval, and we try to explore the links between the two. So the first question is this question about how to combine the attributes of the graph the topology of the graph without relying on the Gromov-Wasserstein approach and the fused Gromov-Wasserstein, which was a little bit too computationally heavy for our test. So, but this is summarized here in the graph underneath. This is a solution. But before commenting this solution, we can have a general view of that. So we need to combine attributes and structure of the graph. But in fact, this is exactly what graph signal processing has been studying in the past 12 years, from the initial proposition of Schumann et al. When they coined the work, up to the recent and nice textbook by Antonio Ortega. We know how to process the attributes according to the structure of the graph. And we have ways to build features to, depending on what we want to focus on, so that the attributes are processed by the structure of the graph. More precisely, so if you introduce the adjacency matrix, the degree matrix, the Laplacian, here combinatorial Laplacian, the degree matrix minus the adjacency matrix, the processing can be, for instance, some function of the Laplacian applied to the attributes. And again, the colleagues from the EPFL, especially Dorina Tanou, Xiaoying with Pascal Froissart and Kressner, they have shown that one useful feature, which is a good way to model signals and also to process signals, is heat diffusion. So here I'm just taking an example from a review paper we published in the Compte rendu de physique about graph signal processing. So if you do heat diffusion from a node somewhere here at the middle on this of this bunny, you will more and more define large scale on that. If you do that exactly on a graph which has communities, you will even be able to extract the communities from the graph using heat diffusion, for instance. So it's a good way to emphasize small structures at a certain scale, which in fact are structures that would appear as low frequency components in the graph signal processing approach. And in fact, it has been already proposed 10 years ago by David Hammond in a paper at Global SIP that this was a good way to build a distance between graphs. So he has proposed this graph diffusion distance. Again, like me before, at the same time, he has a title that's way too long, and his article was not forgotten, but maybe not that often read. And he was proposing that if you are using the kernel, the heat kernel, so the exponential of minus some time multiplied by the Laplacian of the graph, and you are comparing the kernel for a given graph 1 and for another graph 2, then you can compute the norm, the simple Frobenius norm between the two of them, if you have the same number of nodes in your two graphs. And then it's showing that the maximum over all the possible diffusion time of these differences between, this distance between the two kernels gives a proper distance with all the required properties that can be a distance. And then he's exploring here on a simple barbell graph with a perturbation of edges, how the distance behaving. Here you have the distance as a function of the diffusion time. So in a sense, it was okay for graphs with the same number of nodes, and we wanted to see whether it's possible to do the same for graphs with a different number of nodes, and whether it is possible to use the same ID with attributed graphs. Hence, we went to this idea that if we want to leverage all that, optimal transport, diffusion on the graph, and so graph signal processing, we can consider two graphs of different sizes, N and M, they are associated Laplacians. We have features on the source and the target graph, and we can introduce some cost function between the features. This is an open, this is like in the original optimal transport approach. This is an arbitrary choice, but you can take a A2 distance, for instance, between the features. And now we introduce the diffuse features, which are the application of the heat kernel for the source graph to its attributes, and the heat kernel to the target graph to its own attributes. And now you have new features and you are solving the optimal transport coupling, and you obtain a diffusion distance, can be done with a LP norm, between the initial attributed graph and the target attributed graph. And you have mostly two parameters, the diffusion time for the source graph and the diffusion time for the target graph. So the first point is that it's quite, maybe not easy, but it's possible to show that it has good properties. If you define, so this diffusion versus time distance between two distances, mu and nu, and these distances can be taken as representatives of attributed graphs given two diffusion times. If you solve that, you have a distance, which is really a distance. It satisfies all the properties. With the bounds of the distance, we know that if we are not diffusing anything at all, you are not taking into account the topology, and you have just the diffusion, which is the Wasserstein diffusion between the features. If you are diffusing with an infinite time, then you are smoothing out all the features, and you have a distance which is which gives a lower asymptotic bond that we were able to show, which mostly gives you a comparison between the topologies of the graph. And moreover, now you are solving, let's say, a classical Wasserstein problem, and not a Gromov-Wasserstein one, so that computationally it's way more efficient than a fused Gromov-Wasserstein. More precisely, when you want to minimize this thing, you have a sum over the nodes in one domain, nodes in the other domain, instead of having a sum of two nodes in one domain and the two nodes in the other domain. So you go to something which is the power 4 on the number of nodes to the power 2 in the number of nodes. So what we did is to try to use that for the task of domain adaptation on attributed graphs. So domain adaptation is what? Here you have a small picture on the right telling you if you have acquired measurements in blue that you are able to, I don't know, classify, cluster, do whatever you want on that. And now you have a new set of measurements in red, which is not well aligned to your initial data because the measurement has changed, the data has changed, the power of the measurement has changed. It can be fruitful to try to see whether you can move the red points to the space of the blue points so that you have a good superposition of the new acquired data with the previously one, and then leverage what you have done, the classification or clustering task that you have solved on the blue data set, so to do the same thing on the red data set. So they have different ways to solve domain adaptation, and it's known since a few years that optimal transport can be one way to think about domain adaptation. And so we tried to see whether the new distance that we're proposing for attributed graphs using optimal transport is a way to solve domain adaptation between two graphs. That means, for instance, you have one graph here on the left, another graph here on the right, but you say that you don't have the labels for the graph on the right, and you want to transport the labels on the initial graph to the new graph. The two of them here are drawn from the same type of stochastic block model with attributes. So we can do that, and in fact, for this task of domain adaptation, we did some simulations, and so here I will not detail all the curves. So what you can see is that if you are only considering the diffusion versus time distance, is the third curve, which is in orange, this one here. Here, this is a case where you are changing the SNR in the target feature. That means that the more you are on the right, the more you have blurred the target features as compared to the initial features. And the second graph on the right is when you are modifying the structure of the graph. That means here we are changing the features on the left. Here on the right, we are changing only the topology and not modifying too much the features. And you see that the performance in terms of accuracy of the labeling on the target graph using the labels from the source graph is decreasing, but still you are able to classify that using the diffusion versus time distance. better than using only Gromov-Wasserstein or Wasserstein or the optimal transport using Laplace only. Still, we were not able to have better performance than the fused Gromov-Wasserstein approach, which is quite good, but more computationally intensive. And if we want to have the, I don't know if it's the best of both worlds or the worst of both worlds, but if you want to have the computational heavy approach of fused Gromov-Wasserstein while using the proposed distance that we are putting forward as being efficient to combine attributes and topology of graphs, then you obtain the curve that's on the top where you have the best performance in terms of resilience of the blurring, either of the topology or of the feature. And this is here summarized on one specific plan. I don't remember which one in terms of SNR and structure modification, but here you have this diffused Gromov-Wasserstein, which has the best performance. And in terms of scalability, diffuse Gromov-Wasserstein and fused Gromov-Wasserstein have basically the same computational time, the same computational load, while diffusion Wasserstein is lower and scales better. Sorry. So there's still a question here. When in this framework we have a diffusion time tau. If you remind, in the original article by David Hammond, he was using the time which maximizes the distance. And so we had this question, this open question: can we do better than in using fused Gromov-Wasserstein, where the alpha parameter, which is a trade-off between structure and attribute, which is fixed as an hyperparameter? Here again, it was fixed as an hyperparameter, but now we proposed a way to estimate it, because in fact with optimal transport we have many ways to manipulate the data, the distribution. For instance, it has been proposed as a way to create barycenters between data. And so from the original graph and the targeted graph, we can introduce a kind of imposter, something in between them, which is a Wasserstein barycenter between the features. And for the graph, we introduce a random graph so that we have a null model of what's happening on the graph. And we will introduce, so here for the feature, the Wasserstein barycenter, that is the set of features which is minimizing the classical Wasserstein distance between this imposter X and the features of the source graph, and this imposter X and the features of the target graph. You then put this Wasserstein barycenter on a Erdős-Rényi random graphs, and you obtain something on which you can compare your loss. And you want to maximize some loss, which is taken here as a triplet loss. We are imposing that we diffuse the same time on the original graph, the source graph and the target graph. And you want to maximize the contrast between the source graph and the target graph, but now comparing to some null measurement, that is the distance between the source graph and the imposter, the distance of the target graph and the imposter. And now you have a new loss function that you can try to minimize, and it gives you what is the optimal diffusion time of your data. And it turns out, maybe it was a little bit a surprise for us, but still, it turns out that it works doing that. And it's a way to set the diffusion parameter without using the method that was using initially circular validation, like the people were proposing in domain adaptation. That means you take your original classification on the source data, you project that on the target data, then you project it back again on the source data, and you do something circular. But this is good, but the stability of the method is not that good. And when you are optimizing the triplet loss that we are proposing, then here again, with some accuracy performance on some contextual stochastic block model, you obtain here the best parameter. You can even do something more stable by introducing some entropic regularization in your in the setting. But anyway, so the conclusion of this part is that combining optimal transport, or here one technique for machine learning plus the insight of graph signal processing allows to solve in an efficient way some task. Here, the one of domain adaptation between two attributed graphs. So more recently, because our colleagues from Saint-Etienne, they are also experts in machine learning, in a metric learning, not only machine learning. That means the domain of machine learning when you try to adapt the distance or adapt the metric at the dataset that you have. So here, taken from the tutorial of Aurélien Bellet, if you have a set of data in some space and you know that some data, the one with a green edge, should be close one to another, whereas other data, the one with the red edges, should be more distant one from another. You can change your metric. If you have a metric with some parameter, you can optimize the parameter so that you are satisfying the constraint that some elements are close and some elements are distant. So it's a well-known domain of metric learning. And we had this question whether we could use what we were doing before for metric learning. So in fact, it turns out it was a little bit more complicated. So because the focus is really, so there are existing solutions to do to jointly code for the topologies and attributes, but really, if you want to play the game of metric learning on attributed graphs, then you will optimize the learning. That means if I want to use my diffuse Wasserstein time distance, I will compute the distance many times with different tau, and I will optimize tau and change that many times. So it's possible. We have done that on this triplet loss, but it's costly. So we decided to try to have another way both to solve optimal transport and to encode the topology and attributes. That means just computing the heat kernel on some features can be costly. So we have worked so as to reduce that and to have guarantees and publish that in an ICASS paper last year. But it was still too computationally heavy to do metric learning. So what I will propose here is this work about a simple way to learn metrics between attributed graphs that we have presented on the Learning of Graph conference this December. So it's a joint work with Amaury Abrard, and it was a part of the thesis of Yacouba Kaloga. And so the idea, so if you have followed a little bit up to now, to do optimal transport on attributed graphs, we have many different solutions, this Gromov-Wasserstein, this diffusion Wasserstein, but they were not scalable enough to do that. Because here we are summing on things over 4 nodes. Diffusion Wasserstein, we are still solving an optimal transport with the sum over a node in one dimension or node in another dimension. So we decided to do the thing differently. We decided to compute the parameterization of the combination of graphs and attributes by using a graph convolutional networks and try to use the simplest version that was efficient enough for our need. Then we try to use optimal transport, but a reduced version of optimal transport where we compute that only in one dimension by projecting, so the so-called slice optimal transport. And then if we are combining these two elements, 1 and 2, we are able to do the training, the supervised training of the distancing using positive and close examples in our training set. So we have 3 steps, but globally, this idea of doing metric learning for attributed graphs is really to have a simple and scalable model, really in a sense of frugal machine learning, even though it's hard to say that it's frugal when you are training a distance. But anyway, we want to keep the computational load acceptable and the number of parameters acceptable and the scalability of the type of optimal transport that we will use acceptable. And then if that is to be of interest, we will have to focus on a method for classification, which also should be computationally low. We don't want to put that a new, I don't know, a neural networks or SVM. We don't want to train something which is computationally low. So for graph neural network, for the representation, so we are using graph neural networks. So here I'm just summarizing things that you, I guess, already all know. The fact that you can represent the features of a graph by the feature in a data by applying a nonlinear activation function of a weighted version of the data plus some bias. For graphs, we know how to do convolution of graphs. For instance, we can use the convolution in the spectral domain as proposed in GSP. Since there have been many propositions coming from the work of Michael Defferra, the proposition of GCN by Kip and Velling, and the more recent and smarter proposition. So we're not proposing a new architecture for GNN. What we will propose is to use one that has been already shown to be efficient enough and which is scalable in the acceptance that we have before for metric learning. So you know that graph neural networks, they have different flavors using features, attention-based, message spacing. The more simple are features. They are very good application. Just quoting applications that I find very interesting. Here, we really, again, relied on some insight from graph signal processing to find a simple GCN that we can still use to parameterize or to combine this attribute and the topology of a graph. So we decided to use what's called the so-called simple GCN from 2019, which amounts to globally do a graph filtering, then feature propagation with only one nonlinear activation function as compared to stacking different layers of graph, like let's say a deep GCN proposed by Kip and Velling and the variant over that. So simply, this GCN is written as applying the value to the modified adjacency matrix to the power R, so to encode to the R ops in the data that you're applying to the features that has been weighted by some hyperparameter. And doing that, we have a number of parameters and hyperparameters which is limited. The number of the training parameters is only this matrix theta, and the hyperparameters is the size of the P of the output Y of this simple GCN, and R, the size of the neighborhood that we are exploring, so the number of hops that we are putting into that. And if you are doing that, then the output Y can be used directly as a representation, as a distribution. But we take the distribution of Y as a representation of the attributed graph through this simple GCN. The second part is now to use optimal transport, but we don't want to use the previous version of optimal transport because they are too computationally heavy. So we use the version that has been put forward by especially Nicolas Bonnil, sliced and Radon-Wasserstein approaches. That means to say, we know how to solve optimal transport in one dimension. If you reduce your data or your distribution to just one dimension, then finding the optimal coupling from this here distribution to this second distribution from X to Y is just amount to sorting your values. And sorting your value, we know that's just in n log n. It works both for discrete and for weighted distribution. And you just have to sort them and then do the optimal coupling. And so you have a very efficient algorithm to do that. And you can go for the initial distribution, whatever the dimension, to 1D by just doing a projection in some direction of your space. You can show that it gives you a matrix if you take a large number of projections and you try to do a Monte Carlo sampling of this thing. So more precisely, you want to, with this sliced Wasserstein distance, you want to sample directions at random so that you have a Monte Carlo approximation of the usual Wasserstein distance by taking a large number of directions. Then if you want an efficient version of that, or a less biased version of that is what's called the projected slice versus time distance. That means you don't compute the distance only between the 1D projection of your distribution, but you are using the optimal transport coming from 1D, but then you are computing the distance in the original feature space. And this was proposed by Roland and co-author at ISTAT, and it works very well. But still, you are doing a Monte Carlo approximation, so you need let's say a lot of angles to approximate well the slice versus time distance. But in our proposition, we don't want to approximate the versus time distance. What we want to do is to have a parameterized distance so that we are able now to learn a metric which is best suited to the task we will have at hand. So we don't need to have a good approximation of that. We just need to take a few random or practical directions so that we are able to still have a distance and to have a reduced computational load. And we were able, especially Yakuba Kaloga was able to show that if you take, because it's convenient, only the canonical basis vector of your space, and you reduce, you limit the direction that you explore to the number of axes that you have in your data, then it still gives you a distance. And excepted in very rare cases, you are able to distinguish between different attributed graphs. And it is something that is way more computationally efficient than using the slice versus time approach. Okay, and now the distance parameterized by theta, the hyperparameters, which is in the simple GCN, is taken as this restricted projected slice versus time distance between the two graphs being encoded into the GCN with the parameter theta. Now we just need to train that. I'm skipping a little bit the details about that, but we just rely on the classical literature about metric learning. We know that depending on the task, we need to specify the loss function, which is suited to the task. Here, the task, because we focus on the KNN classification next, we give a variant of Navier Cloud analysis, that it is a Navier class cloud metric learning. Basically, we are trying to maximize the probability that each graph is in a group having the label of the same graph. We have a data set of labeled graph, and we want that the graph with the same label are close one to each other according to this probability grid on the exponential of the minus the distance of the graph. So this is a general view of the training of this simple graph metric learning model. We are using this loss function. We are computing the distances according to this property of restricted slice projected versus time distance. We have only two hyperparameters, P and R, and the complexity can be shown to be this one. There is a complexity for the optimal transport training and the complexity for the GCN on the other side, and this is the space complexity. And okay, now quite classical and always a little bit boring to comment during a talk, but we played the game of doing that on a different classical data sets from in graph learning, both with continuous node attributes or discrete node attributes, different sizes, not very large scale, because the idea is already to see what can happen on this data set. And if you do that, especially for KNN, we have both here in the case of data sets with with discrete attributes, and then on the next slide with continuous attributes, we have good performance, not super good performance. The idea is that we are performance which is comparable to more costly methods such as NetLSD or Fuse-Gromov, the approach based on Fuse-Gromov versus time, for instance. We even have tried to do the same thing by then training a SVM, even if it's not the focus of the work, but we can use induced distance to train a SVM, and then we have a performance which are quite correct, again, in the two types of graphs that we have. But the good point is now, okay, this is for illustration purpose. If now we are using one visualization technique, here t-SNE, on the distance that we are proposing as compared to what happens when you are using the Wasserstein-Weisfelder-Lehmann kernel. Maybe, depends of how you see it, maybe we have a better distinguish between the groups. But anyway, what we obtain, and that is what the main point of this idea of studying the scalable method, is that we have a scalability which allows us to go up to the number of a graph, which is 2 to the power 8 with a linear scaling in log-log, wherever if you are using POT for optimal transport over a certain distance, it will increase and we are not able to scale more. So I guess I'm almost over time, so I'm skipping the ablative study, but the ablative study just tells you that if you are not using this newest Nearest Cloud metric learning or this slice and projected restricted versus distance, we have a not so good performance. So the time to conclude, in addition to just the conclusion of the method that we have proposed, we are just instance of manners to combine graph signal processing and optimal transport to solve tasks of machine learning of attributed graphs. The idea is that indeed we are able to, when focusing on simple method and specific objective, we are able to propose the method with computational cost, which is at least reduced or controlled. And the way forward is that I think we still have many things to do using insight from GSP in machine learning to improve feature extraction. And also the thing that we are working now is to have more explainability of these graph-based machine learning methods. So I thank you for your attention, and I'm open to all questions, naturally.
Thanks, Pierre, for the nice presentation. So yeah, the floor is open for questions. I see there are already some in the chat by Faize. If you want, you can unmute. Otherwise, I can, or we can have a look. So I see the.
Yeah, so I see a question. So the relation to the Kullback library divergence, in fact, I think there have been works trying to show that you can relate distances between information distances and distancing from optimal transport. A few years back, 2 or 3 years out, there have been works. So there are relations, and in a sense, it could be put under a more general framework where you will have globally. You can see some of the information theory-based distances connected to optimal transport. And
I just wanted, so yeah. First, thank you very much for the interesting time. I just wanted to know if they have same origin like Kullback library divergence, or they are from totally different perspective. And
initially, they are from totally different perspective, but I remember that I've seen articles who were showing that there are links between them. But I've not delved much into that. But initially, they are from different perspectives. As you see, one is from this Monch-Kantorovich problem. So it's really this perspective of moving distribution, and it was a way to solve to have properties on PDEs, and it's also the thing that opens the way to linear programming in computer science and applied mathematics, but I think there are relations that have been drawn by other people.
Okay.
And you have this question about, yeah, we are mostly in clustering within graphs. Yes and no. If you want to cluster between different graphs, it has applications in chemistry. For instance, in chemistry, you want to have a way to say that these molecules will be closer to these other ones, and there have been a lot of work by trying to predict what is the properties of molecules based on their graph coding. So it has been done since a long time by in the chemoinformatics, chemistry plus computer science, and this has been also revisited by people from machine learning when you try to, for instance, predict the behavior of drugs And for instance, Sandeep Chepuri has worked on question about drug repurposing, and you want to compare graphs. Another application will be to say, let's say you want to, you have something like the Wikipedia who has been well labeled at some time, and now you have another encyclopedia or another language at another time, and you want to not redo the work of classification and project the password of a classification to the new instance. You will not have the same nodes, you will not have the same edges, but you still will have the same basic structure of the thing. It can be also done for social networks. And so there is this interest to be able to do the domain adaptation from one graph to another in this type of data. Or you can do that on meshes. It has been, in fact, done already by people for registration and to follow movements of meshes from one image to another one. I'm not way familiar to that, but it has been done.
And Faize also had a question about diffusion Wasserstein.
Diffusion similar to moving a source surface to a target surface. Yeah, in fact, it is optimal transport is one way to do transfer learning also in machine learning. That's been put forward by people as one way. Yevgen Redko has worked on that at Saint-Etienne a few years back. So yes, you can see that moving something to another one, doing the minimal cost. Just the idea of this diffusion Wasserstein was really to say you need to encode both attributes and topology, and here it's done by diffusion.
Then I think George also had a question. So George, if you want to unmute, go ahead.
Yes, thanks. Super exciting talk. Thank you. So the question was, do all of these methods assume some kind of graph matching, that is some kind of isomorphism type matching, like the seeded type matching that Kerry Priebe and others have worked on? So in other words, you find some kind of alignment first and then you apply these methods. Is that the assumption?
No, we don't use any alignment before. In fact, the graphs are not aligned at all before, and the idea is to see whether this approach is able to. This is not something we have done a lot, but it could be one way to see whether we are finding the good alignment of the graph. So clearly we have some, not instability, but when you are aligning a stochastic block model, for instance, you can have these things that you are permuting block 1, block 2 in one graph, and block 2, block 1 in the other graph. But we are able to solve this these models without doing the alignment before.
Okay, but can you then impose certain restrictions? Like in the seeded graph matching, you can have, let's say, certain pairs of vertices that,
yeah, I think
you know, a priori that
I think we could, and if we want to solve the graph alignment problem without this instability that you can swap between blocks and things like that, I guess it will be a sound way to do that, to say you have examples that you want to align, and then you try to align the rest of that. I guess it should be possible to do that. We have not done that, but there's no theoretical difficulties, theoretical impossibilities. I guess there will be a lot of difficulties to do it, but there's no theoretical impossibilities to do it.
Excellent. Thank you very much.
And about I see that there are code implementation. Yeah, both works. We have an implementation which is somewhere on the GitHub. This is referenced to in the articles.
And also the presentation will be posted on the IEEE.
Yes, I will share the presentation.
Yeah.
Pleasure.
Yeah. But it will be on the YouTube channel, also the video at least. So
okay.
The slides we can put on the website of the DIGA webinar series.
Yeah, I can put on my website, but I will share the slides anyway.
Fine. Pierrick also had a question about if you have two graphs with the same topology but different signals, and then the mask could be moved along the edges. Have you studied this case?
Two graphs, same topology, but different signals. Then yes, if we have the same topology and different signals, we mostly will have a distance, at least in the initial work, the first work, we mostly have a distance which compares how far the signals are from one graph to another one. In a sense, excuse me, it should be. Let me up. Sorry, I wanted to go back to a previous slide. In a sense, that's the thing we were trying to probe when we were doing these experiments. Here we have so this experiments when you are zooming on the left. Here we were justly modifying the features and keeping a topology which is not that far away one from the other. What we have not done at all is to say the thing that's interesting that you are saying. That means that possibly we could rely what is the distance that we obtain to some really moving of the feature on the graph. Here we have a distance, but we don't know how it changed with I don't know a certain moving of the masses along the graphs. I don't know. This would be an interesting question.
So that would relate more to that you have a PDF on the graph or something like that, right? Suppose that you have distributions on a graph that you want to transport using where the cost is related to the weights of the edges.
Yeah, maybe it could be.
That's a different problem, I guess.
Yeah.
Faize also had another question on attributed graphs being kind of weighted graphs.
Encoding feature, yes, indeed, it's a new weighted graphs where we are putting them together, and indeed the idea was to see whether it was a way to say something still relevant for the graph. But yeah, we can see it like that. But really, the idea is coming initially where the slide here, but saying okay. Yeah, this thing, if you are diffusing the features on a relevant scale on the graph, you are combining both something of the topology and something of those features.
Yeah.
And does it work for rotation on one graph? But in fact, it could work. At some point, we had done experiments where we were using as features the coordinates of the node, for instance, coming from a 3D representation. You take a mesh, you have as attribute the 3D coordinates, and then you can, no, I don't have the figure here, but you can morph and try to see what is optimal displacement from one weight mesh with weights in some source space to a target space, which is a different weight. So you can, let's say, for instance, transform this bunny in this social network and try to find what is the optimal coupling to go from one to the other. Mm-hmm. And so rotation will be just one different geometric transformation.
Okay, thanks. Any other questions? If not, then I think we can wrap it up here. So thanks a lot, Pierre, for your nice presentation and very interesting work. And then we'll meet again in 2 weeks. So same time. So Gerald Mats will give a presentation then. So thanks for attending and see you all in 2 weeks.